Today we are here with the Unitary Group, and they will be talking on the topic error mitigation and mimetic. So I think Jordan, yeah, welcome to LIAS 2024 program, and I would like to hand over to you for the session.
Thanks very much. Yeah, so I'm Jordan, Jordan Sullivan. I will be just jumping right into my talk here. Can everybody see my screen?
Yes.
Okay, great. Ready, I'm just gonna move this Zoom thing. So yeah, today going to be talking about quantum error mitigation and open source software, specifically the mimetic package, which my colleague Alessandro will be talking a little bit more in depth about after I give my talk. So yeah. First off, we both work at Unitary Fund, and just a little bit of background on what our company does. It's a nonprofit, and we are aimed at creating quantum technology to benefit the most people. We want to expand the pool of people working on quantum technologies and make sure that they're widely and equitably distributed. So mainly we focus on open source software and giving out micro grants for projects that are in this space, in the quantum open source software space. And the kind of broad vision here is to create a more inclusive quantum open source community. We want to support new projects while researching and developing more tools to accelerate quantum technology. I think I saw a couple of hands. Did people want to ask questions? I'm not sure who raised their hand first. Well, if anybody has questions, feel free to put them in the chat, and I'll try to keep an eye on that as well. Cool. So Unitary Fund, we do kind of three main things. Like I mentioned, we have this micro grant program, which we fund kind of exploration to work on quantum technologies, and we grant these to people around the world. There's no restriction on.
Then you can continue.
Great. Oh, okay, great. I think there's a little bit of a lag on the internet connection for me, but yeah. Cool. So microgrants, and then secondly, we have our own research to kind of help the quantum ecosystem overall. So today, again, I'm going to talk about MITIC, which is this description is slightly off, but MITIC is a quantum error mitigation software. And we also have Metric, which is a community platform for sharing quantum benchmarks. So like, what is the current performance of the best quantum hardware in the world? How do we compare progress over time in this field? Then lastly, our community. There are many aspects to this, but we have an open source quantum tech community which runs hackathons and events in our Discord, and I can share a link to the Discord, or maybe Alessandro can drop that in the chat if people are interested. You're more than welcome to join. There's lots and lots of different channels always going on different topics that people are getting into, and to kind of different levels of expertise too. So who is the team? This is us. This is the whole Unitary Fund gang. Pretty small group of people, but we're small but mighty. And today, these are a couple of our past employees. Today, it's going to be myself and Alessandro there at the bottom. We're going to be giving this talk today. So actually, before I jump into the talk, I was curious to find out a little bit about the audience. So I was curious, could people raise hands if they are if they've been studying the whole like term during this this course, I guess, or if anybody's like brand new today to quantum. Yeah, I guess like raise your hand if you've been here like the full course.
Hello.
Was that a question?
Hello.
I think I'm getting some background noise, but cool. So I'm guessing a fair amount of people have been here during the full course. So let me just ask a kind of broad question. Who has heard of quantum error mitigation before? You can raise your hands if you like for this one as well. Anybody else? I'll give like maybe 15 more seconds. A couple people. Very nice. So whatever your background, I think it's pretty interesting to learn about quantum error mitigation and kind of how it fits in with the general trajectory of the field in quantum computing. So I will just jump into it here. So quantum error mitigation is essentially the idea that the quantum devices, the quantum computers that we have in our available ecosystem are quite noisy, very noisy, but we still want to use them and see if we can get anything useful or scientifically interesting out of them. So there are many different types of errors that come up when you're trying to build a quantum computer. So one would be incoherent noise, and so this is noise where you can't easily, you can't reverse it. It is something that messes up your whole computation in a way that you can't simply undo. Then we have spam errors, as they're called. So that's state preparation and measurement. So basically, when you're trying to initialize a quantum computer in a particular state, like I want to create a qubit in the 0 state, but actually what I prepared was like slightly off from that state. And then measurements, there are errors that can come up while you are trying to read out what the state of your qubit is. Let's take a quick look at the chat to see. Cool. And then another type of error that you can run into is crosstalk. So this is when you're trying to affect one qubit, but you end up accidentally affecting like neighboring qubits or maybe qubits that share the same resonance somewhere else in the circuit. And so you change the overall state of your computation in a way that you didn't intend to. Then there's also calibration errors. So basically where I want to say, I put my qubit in this 0 state, and I want to calibrate a gate to flip it from 0 to 1. I want to calibrate this like X gate. But when I actually do that, I try to rotate the qubit around the Bloch sphere, but it actually goes like a little bit too far. And so I'm thinking that I'm flipping it, but I'm actually doing like this extra rotation. So that's a calibration error. Many other types of errors in quantum computers, really endless types. I used to work at a quantum hardware company, and part of my job was modeling in simulation different types of errors that can occur in a quantum computer. And there are so many different types that you really have to kind of like simplify more and more as you get kind of higher up the stack. But it's definitely a very important field to be improving our resilience to. So what does quantum error mitigation actually do in this situation? So as many of you probably know, if you've been in this quantum course, all quantum algorithms are probabilistic. So you have to repeat them multiple times, and you're sampling from a probability distribution of the end quantum state in your quantum computation. So you would hope that you have this ideal distribution when you sample from it, when you repeat the circuit many times. but what you actually measure is some noisy distribution, which is it's maybe got like systematic error where it's shifted away from the ideal, and it's like more spread out. So there's more of this stochastic error that is not quite as peaked as in the ideal case. So what does quantum error mitigation do? Well, in some cases, it would give you a result that looks something like this, where we have managed to shift back to the ideal distribution, and the output state may be more spread out, but the average for this, the expectation value of this like operator, it doesn't matter to any operator, is still on average like the ideal or closer to the ideal. Feel free to ask any questions about that if it's not quite making sense, or if there's a term I've used that you're not familiar with, feel free to put it in the chat or raise your hand. Otherwise, keep going. Okay, so there are many different types of quantum error mitigation, or QEM, as we sometimes call it. So these really range from the different types of computational tools that they use, but generally I would say like what most quantum error mitigation schemes have in common is that they are using classical computers in some sort of either pre-processing or post-processing of the data of a quantum computation. So in the case of zero noise extrapolation, we're going to talk a little bit more in depth about that one, so I'll leave that one for later. We've got these symmetry-based techniques, except that I messed up this letter here. Let me see if I can fix this. One sec. So this is clear for folks. There we go. Yeah, we have these symmetry-based techniques where you use certain properties that you know about the quantum state in order to take advantage of that fact. You have something like probabilistic error cancellation, and in this case, you have another called dynamical decoupling. This is where you send pulses through your machine to try to decouple the computation from the environment or external noise. And this includes inserting extra gates into your circuit. So this is one of the cases where it's like pre-processing. So you have the circuit you want to run, and then you're adding in extra gates to try to reduce the errors. And then you have like learning-based methods that are more machine learning focused. So, and this is only a small subset of the total number and kind of diversity of quantum error mitigation schemes, but I would say definitely the most common is zero noise extrapolation, and probably these two are also among the more common ones, but there's kind of new ones being invented any time. Maybe you'll invent new ones. So if you have heard of quantum error mitigation, then you have probably also heard of quantum error correction. And if not, totally fine. But how do we think about the difference between quantum error correction and quantum error mitigation? And just before I go on, if you're kind of interested in this topic and kind of developments in the field of quantum error mitigation, there's this really great report from the company Riverlane, which is focused on quantum error correction. And they're based in the UK. They put out this pretty accessible report about it. So this other paper here is a result from a hardware team who demonstrated a small quantum error correction code. So what's the relationship between quantum error correction, quantum error mitigation? So first off, error correction encodes logical qubits into many physical qubits. So In classical error correction, kind of in normal computers, our error correction can be pretty simple. You can essentially just, like, let's say I want to send a single bit to somebody, like I want to send a 0 to someone, but there might be errors along the way, and so maybe it gets flipped to a 1. That's not great because like there's no real way to recover what the original state was. So I could just send extra copies, right? I could just say, I'm going to send like 0, 0, 0, and then I'm going to send that. And then I would need 2 of the zeros to get flipped in order for the whole message to be lost. So this is kind of the intuition for what you want to do in quantum error correction, but if you are a little bit familiar with quantum mechanics, you'll know that you can't actually copy quantum states. That is the no cloning theorem, so you're not allowed to do that. But what we can do is essentially entangle a bunch of qubits together and let them share the logical information between them. And then there are certain properties that an entangled state like this that is encoded into a quantum error correction code. There are certain properties that we can make use of to correct errors that occur. And there's a lot more to it than that. There's a lot of really fun math and different computational techniques that come into it, but that's kind of the overall way to think about it. So this is, we have this idea of like, let's say like one logical qubit encoded into like, 100 physical qubits, for instance. In error correction, we have these intermediate measurements which produce syndromes. So what I mean by intermediate is that it happens during your computation. So like maybe one time step goes by and then you perform a quantum error mitigation step. You perform a quantum error correction step. You measure all of your qubits, or you measure like a subset of your qubits that you're doing your quantum error correction on. And then you try to infer what errors occurred in your computation based on those syndromes. So you kind of have messages about, oh yeah, my cat is here, so she'll probably be a little bit distracting. Apologize for that, unless you like cats, in which case you're welcome, I guess. So quantum error correction, you have these measurements, you produce syndromes, you try to guess where the errors happened, and then you correct those errors based to the best of your ability. You say, I think there was an error here, I'm going to flip it because I think it got flipped as an error. Now, quantum error mitigation is different. Often you'll be performing multiple different noisy computations. And so you'll perform like the whole computation, and then you'll say generate a slightly different circuit, and then do that many more times. And then you'll collect the results all together, and then you're going to try to infer the ideal ending expectation value. So just to kind of broadly explain, error correction is something that needs many high fidelity qubits. So you need qubits that are very low in their error rates. They're really good physical qubits. You need a lot of them. A lot of estimates will put this number around, like if you want, say, 100 logical qubits, so qubits that you can run a quantum algorithm on, often estimates are like that you need around 1 million physical qubits to do this. That there are some variation in that. Some say that you can do that with like 100,000 qubits, for instance, but it kind of depends on how good your quantum error correction code is, like how much you can take advantage of the particular pattern of entanglement in your encoded logical qubit. And then quantum error mitigation really needs few noisy qubits. So the individual qubits do not need to be very high fidelity. However, you can't really do it on a lot of qubits. There's kind of inherent limitations on quantum error mitigation. It doesn't scale well. But if you have a relatively small number of qubits, you can use quantum error mitigation. Okay, so what is zero noise extrapolation? Very basically, we want to scale our noise up and then extrapolate back to the zero noise value. So I'm going to talk about what that means. So first of all, this is an equation that governs how our quantum state will evolve in the presence of noise. So if you've never seen this one before, it's called the Lindblad master equation. And if you're familiar with the Schrodinger equation, this is just like the matrix form of that, but with this extra term for noise. And so this L of rho, this is going to be the particular function of the noise in our system. And then this lambda parameter is going to be what we use to scale the noise up or down. So if we wanted to plot the expectation value here as a function of lambda, this noise parameter, what we want is to be able to get down to this zero noise area, but in practice, this is inaccessible. We don't have qubits that are good enough to have such low error rates. So what do we do? Well, let's just simulate with the best that we can do. Let's say we assign kind of the baseline circuit 1 in our lambda diagram here. And then we also do additional simulations, or rather we do additional runs of our quantum circuit where we increase this lambda parameter. And what you can then do is extrapolate back to the zero noise value. And so in this case, it's just using a linear function, just a straight line. There are many other options that you can try to estimate your zero noise value, because it's not necessarily always the case that as you scale this noise parameter up, the function is going to be a simple like linear function. It might have some other more complicated form. So, it's important to test out different ones. So then we can use this. We can use the equation that we estimated to get this line and just plug 0 into the equation to get our ideal or noiseless value. Okay, so kind of conceptually, we might understand, all right, so you are going to run the same quantum circuit multiple different times. You're going to run it with, artificially increased noise, and then you're going to try to extrapolate back to zero noise. But how do you do this? How do you think about scaling the noise up? So there are different ways that you can do this. One of them is called pulse stretching. So in quantum algorithms, in quantum computers, pretty much all of them are going to control qubits using pulses of some kind, whether it's like a microwave pulse, a laser pulse. You are using some sort of quantum interaction to change the state of your qubits. And so a pulse like this has some, variance with time. It's going to have a particular amplitude at a particular point in time, and it lasts for some duration. Like maybe it's a few microseconds, maybe it's on the scale of nanoseconds. But generally, you would think if you are trying to build a quantum computer, you probably want your gates to happen relatively quickly so that you can have a faster computation. But in this case, we want to do the opposite, actually. So we're trying to artificially stretch out how long the pulse is actually running. We want to make sure that it's the same pulse, but it's just stretched out in time. So if this pulse represents, for instance, some circuit like this, where there's a gate on the first qubit and then some sort of interaction, and another gate, then we could kind of imagine this as being the same circuit, but kind of stretched out in time, if we think of time on the x-axis. And the reason that you might expect this to increase the noise is that it gives your qubit kind of more time to decohere. There are, the longer you wait in between sort of operations in your quantum computation, or rather like the longer that your qubits have to be alive, the more chance there is for them to decohere. So this is a way you try to increase the error. Another way is called unitary folding. So unitaries are just the operations that you can do in a one-way quantum computer. So this is anything that doesn't include measurements, for instance. So measurements would not be unitary because you can't just reverse them. Whereas everything else you should be able to reverse. So what unitary folding does is that it takes these operations, takes these quantum gates, and then it will just insert essentially kind of mirrored copies of the gates that are in the circuit. It'll insert their conjugate transpose, so they'll just like the inverse of the gate. So they should cancel out logically. The overall computation should have the same logical output at the end. But because we're inserting extra gates unnecessarily, as long as these gates don't get taken out in the compiler step, then we can be artificially increasing the noise in the circuit by inserting these extra gates. They shouldn't change the outcome, the final outcome of the circuit. Okay, so how do we run quantum programs in practice? So I'm pretty sure this is supposed to say user. I apologize for some of the letters got a little bit messed up in the slideshow step. Okay. There we go, user. So user, like yourselves or me, is going to be writing a quantum program. If you have run these on existing open source software platforms, you might have used something like Qiskit. You write your quantum program, and then you are going to send that program off to either a hardware provider, so maybe you're using like IBM or IonQ, or any number of these devices that exist and are accessible through the internet. And you could send it to an actual device like that, real hardware, or you could send it to a simulator. And by send it, I mean, often the simulator might just run in your laptop or in your computer. And so in that sense, you're not like sending it anywhere. But in the case of hardware, you probably are sending it like through the internet to some device somewhere in the world. And then on this device, it will execute, actually run the quantum program that you have specified. And then you get results back, and you probably want to be able to do something with these results to infer the answer to your computation. Now, if you want to run quantum error mitigation, and in this case, I'm kind of specifically referring to MITIC, but this would be the case for a lot of different quantum error mitigation techniques. What changes is this middle step. So we've written our quantum program. We don't have to do anything different there. Then in the quantum error mitigation step, we're going to generate intermediary circuits. So if you remember let me see if I can go back. In this picture, each of these different lambda values represents a different circuit. So you could imagine they could be either stretching this pulse for longer and longer times. So like maybe 1 would be this pulse here, and then 2 on the lambda scale might be this one, and then 3 on the lambda scale could be even longer pulse. And each of those are actually different circuits. They're running different quantum programs. And then similarly with this one, you might kind of double fold over your quantum gates once in the case of, lambda equals 1, or rather, this corresponds to no folding, just the original circuit. And then you might fold them, for 2 lambda parameter, and then 3, etc. And so that's going to insert more and more gates. And so all of these are going to be different circuits. So when I say intermediary circuits here, that's what I'm talking about. So again, these are going to be sent off to a quantum computer. Often these will be sent out kind of, in a sequence. And you run them, get the results back. Again, of course, you can run this on a simulator if you want, depending on the size of the computation. Most quantum simulators can't get much beyond like 50 qubits or so, because every time you add a qubit, as you might know, that doubles the amount of memory you need in order to actually run the computation. So in this case, when you send your intermediary circuits off to the hardware or the simulator, you can execute them, and then you get back these noisy results. So a set of results that have, varying levels of noise. Again, just kind of focusing on zero noise extrapolation. It works a little bit differently for different quantum error mitigation methods, but for zero noise extrapolation, you take all of these noisy results and you are going to infer back to what you think the ideal value was. So again, in this case, you're going to take all of these data points here and infer this red dot back. And so I talked a little bit about quantum error correction and kind of how we think about quantum error mitigation with respect to quantum error correction. So one way to think about this is that we might try to mitigate errors on encoded logical qubits. So instead of operating on the individual level of those physical qubits, to try to mitigate errors on the physical level, you might actually try to mitigate errors on the logical level. So if you have this big entangled state that represents one logical qubit, then we might try to mitigate error overall on this whole qubit. And so one way to think about this is in a paper that our colleague Misty and several other folks wrote last year, which is called Zero Noise Extrapolation on Logical Qubits by Scaling the Error Correction Code Distance. So the error correction code distance it essentially is how big that entangled state is that you are encoding your qubit into. So scaling it up, making it bigger, and seeing if you can use that to mitigate errors back down to what it would have been your ideal state of your logical qubit. And this paper is quite interesting. So if you're interested in this type of thing, do feel free to check that out. I think it gives a relatively a little bit more accessible of an introduction to these things. So that's worth seeing. And then there are kind of always new papers coming out. I believe this one is from earlier this year. Which is called fault-tolerant quantum error mitigation. So if you read, I think something was just off of mute. Did you have a question, Frank? It's probably an accident. Yeah, so fault-tolerant quantum error mitigation. So fault tolerance is probably a word that will become more and more common over the next couple of years in the quantum computing field. So fault tolerance is something that you can think of in contrast to noisy intermediate scale quantum. So NISQ, if you've heard this term, this is the stage that we've been in for the past few years, where our qubits are pretty noisy. We don't have too many of them. So intermediate scale, it's on the order of like 100 qubits, and noisy, they're not qubits that are high enough fidelity to do quantum error correction on. But when we get to the point where we can do quantum error correction, when our qubits are high enough like physical fidelity in order to do these things, where as we increase the size of our entangled state that represents our overall logical qubit, then we should be getting an exponential decrease in the overall logical error rate in our computation. So this is called the threshold theorem, and this is what fault tolerance means in quantum computing. So fault tolerance is actually a term that comes from classical computing. So just very basically, it's the ability to tolerate faults in your computation and still be able to recover what your end result was supposed to be. And so in this case, this is an example of essentially combining this fault-tolerant regime. So we've got pretty high fidelity qubits, and combining that with quantum error mitigation. So some people currently think that we are in some researchers would currently say we're in a little bit of a different era of quantum computing than we've been in the last few years, which some people are calling early fault tolerance. I think some people are also calling it NISQ. It's like mid-scale, quantum, but I honestly don't remember what the M stands for, but, it's kind of moving from this like small noisy qubits into these like many very high quality qubits. There's kind of this intermediate stage, and combining quantum error correction, kind of like the hardcore version with these big entangled states, and then the kind of quantum error mitigation. This is the regime that we're kind of coming into now, where we want to combine these things together. And then there's a paper that just came out like a couple of months ago that is specifically about the quantum phase estimation algorithm, which you may have learned about, and how you can combine quantum error mitigation with these kind of like early fault tolerant level of qubits. But generally, like, these are very open questions. We don't know exactly the best way to combine these things. We don't know like at what scale we should use them. So yeah, again, if you're interested, feel free to check out these papers, or join our Discord, ask questions, anything like that. Okay, so I'll just talk a little bit about MITIC quickly. And then I'll have a few minutes open for questions, and then I'll hand it over to Alessandra after that. So MITIC, the toolkit, it's a Python library. It is intended for implementing error mitigation techniques on quantum computers. So one of the mitigation techniques that we just looked at in this talk was zero noise extrapolation, and that's the most popular one on MITIC. So as we've said, current generation quantum computers are noisy. They interact with the environment. Gates are not perfectly implemented, etc. So we want to compile our quantum program in a way that's going to mitigate that, right? So we have a number of these different techniques that exist in MITIC, which you can check by importing MITIC in Python and looking at the QEM methods here. So ZNE, this is the one we've been talking about. And there's also probabilistic error cancellation, and then many more. And we're kind of constantly adding new techniques to it so that you can check them out. And then there's always a paper that's referenced, where the scientific article came from. So how do you actually use MITIC? It's really doesn't take too many extra steps. So if you have some circuit that you want to run, like you have the circ circuit, so this is just, let's entangle 100 qubits together with this, or rather, no, these are just X gates. Just put a bunch of X gates on 100 qubits. Then we wanted to run that. Well, normally we would just, have some execute function, whether that runs it on a quantum computer. In this diagram here, we have this execute step. So, it's just send it to the quantum computer or send it to the simulator. And if you want to add MITIC, you would do something like this. You import mitic.zne through noise extrapolation, then execute with ZNE, and then you insert your execute function. So like the syntax isn't super important right now, but this is generally how you would interact with MITIC. And so if you didn't have any quantum error mitigation, you might get an error of like 25%, which is quite bad, obviously. But if you add quantum error mitigation, in this case, if you add ZNE, you can get a really substantial increase, improvement in your error rate, so substantial reduction in your error rate. So it's going to depend on your particular problem, like how many qubits, what the algorithm is, whether ZNE will be helpful or not. But you can get a pretty good improvement in a lot of cases for really small circuits. So we've already seen here that you can use circ with MITIC. You can also use all of these other frameworks compatible. So you can use Qiskit or PennyLane or like PyQuell or Amazon Bracket. Any of these are accepted by MITIC as ways that you can define your quantum circuits. And so if you're interested in this work, if you're interested in anything related to quantum open source software, and you have a particular project in mind that you'd like to build or one that you're already working on that is relevant for the quantum ecosystem, then feel free to apply for a micro grant, and you can do that by following this link here, which maybe Alessandra can also share in the chat or scanning this QR code. So yeah, we just hit 100 microgrants this year, and in 31 different countries, and several hundred papers that actually cite research that was done during these microgrants. A lot of people create new libraries. Some people even created new like startup companies and a new nonprofit. So there's a lot of really cool stuff that can come of these types of projects that we choose. And so that is a good way to try to get involved as well. And that is all from me. So I will go ahead and say thank you, and I'll take questions if anybody has them now. It can be questions about the talk or, generally quantum industry or my background, whatever. Okay, well, it doesn't sound like there are any questions right now, but I will keep an eye on the chat in case. We've got a question here. So what are the main challenges in implementing error mitigation techniques in practice? Yeah, good question. So some of the main challenges can be, well, kind of like I said already, they don't scale. So you can't really do them on really large computations with many, many qubits. Another thing that might come up is that you have to choose parameters to use in your quantum error mitigation scheme, and figuring out what those are can be quite challenging. So in that equation where we were estimating back in zero noise extrapolation using these data points that we have to get the expectation value that is in the zero noise case. We had to guess what form that function takes, and sometimes you just don't know what that form is, or maybe like it looks like it's just a straight line or it's some sort of like polynomial function up until as low as you can get the noise, but maybe at the end it goes like totally wonky and like it doesn't look anything like what you thought it did. So there are many different challenges, but it's a very good question. Yeah, and maybe Alessandro wants to say more about that.
Yeah, I think you covered the two most important one. I think something that to understand in the beginning for error mitigation is that it scales exponentially. So it's good for like the beginning of the near term scale of quantum computer, but in the very long term when we will have large scale computation, we will either need error correction or those hybrid approach that Jordan was talking about at the end of that talk. And yeah, regarding choosing the parameter, I will actually go through that in my demo. So yeah, that's a very good point as well. Very good question.
Well, thank you very much, everybody. And I will hand it off to Alessandro with that.
How does, I see there is another question. How does zero noise acceleration work in MITIC? It's a great question because it's exactly what the second part of this is about. Let me share the screen first. All right. We'll try to keep an eye on the chat, but at the moment, I don't know where that is. So yeah, maybe Jordan, let me know if there is any specific question. So I hope you can see the screen. So this session is going to be more hands-on. Yeah, thanks, Jordan, for introducing the theoretical concept behind error mitigation and some error correction. And in this session, we will actually go on a more practical approach and actually write some Python code. So maybe on a similar fashion as Jordan was asking in the beginning, if I can get some emoji reaction on how many people are familiar with writing software for quantum, like using Python and like using quantum packages for Python. Okay, I see very few thumbs up. So I'll try to go slow and more in details on the different steps. So in the page you can see here on the screen right now is the documentation of MITIC. It's quite in detail, if I say so myself, as one of the maintainer, but yeah, you can go there and find the user guide with the basic concepts, and you can learn about this concept directly there without going through the original papers. All the techniques that Jordan was talking about, you can go to the section and learn more about it in details and specifically how to use them in MITIC. You can learn about examples with practical applications where people from the community had a particular need to run quantum error mitigation and they applied to their problem. Or for example, they were running on some particular backend and they showcased the error mitigation on that backend. For example, the one you see on the left, like on IBM quantum machines. Yeah, you have a tab with the API docs. So the function you can call in the MITIC package, we will go through some of them. Then I will also talk a bit about, if you, after this session, you get passionate enough about quantum error mitigation and you want to contribute to MITIC, I will explain how to do it. Right, so you should be able to see my editor here. Let me know if you don't. I will try to get the chat somehow. Don't know how. Yeah, maybe I'll just make it very small here. Okay. Works. I will have to switch every once in a while. I'll do that. So, okay, first of all, Meetic is a Python package. So you will have to create your own Python virtual environment to run Meetic in. And after that, is as simple as running pip install Meetic. So that's the way you install packages in Python, and installing Meetic is as simple as this line. I will not run it in my case because Meetic is already installed. So let's say the example that Jordan was referring to by the end. Let's say you have circuits you want to run on your, like a quantum circuits you want to run on some quantum computing. But it's noisy. The quantum machine you have is noisy, and it gives you a result that is not the ideal value. So you want to run error mitigation on it. So that's the use case. Now, for the sake of this example, let's say the circuits you want to run is a so-called benchmarking circuits. So a circuits that we already know what the result of the computation is, but we use it to evaluate the error mitigation technique itself. So in this case, we know that if we generate a benchmarking circuits, we will end up with something that is equivalent to the identity in the ideal case. But it's not as simple as the identity. So if we run this cell here, we are generating a circuits on 2 qubits. And you see it's like a big complicated circuits with lots of different gates, square root of poly X gates, swap gates. There are some identity gates as well. There are some like idle times here. But we know that theoretically this is constructed in a way that is equivalent to the identity. So if we run it without noise, then we should get as a result something that we expect the same from the identity gate. So let's say we start from like 0-0 state, then we apply the circuits, we should get back the 0-0 state as well. So not that in this case, so Meetic supports multiple languages to write quantum circuits, including Cirq by Google. And in this example, I will use mostly that. So all the circuits you will see here are written in the Google Cirq language. And also, yeah, feel free to stop me anytime with questions, or write them in the chat. It's a bit hard to, like, if you are in front of a computer and you want to run this on your machine, I think it's a bit hard to do it in live because you will have to copy the cells, but I can share this notebook afterwards by email, and Henry can share it to everyone. So, okay, we have these circuits. We know that it's equivalent to the identity. Now let's actually test it. So let's say you have a real hardware device. For example, you are on IBM Labs and you want to run this on a real device. Then you'd run the code that is commented out here, and you'd get a result at the end. Now, what we usually do when we test things, and when things are on a smaller scale, we use a simulator of a quantum computer. So we don't need to really run things on the real hardware, but we can run things on the same machine that I'm using right now. And in this case, I'm running these circuits through the simulator that is provided by Google Circ. So it's a classical simulator that runs a density matrix simulation of the circuits. So we start from the 0, 0 states, and we are measuring also the 0, 0 states. So, and as I said, this is equivalent to the identity. So the probability that we get this state is actually 1. So the true value that we expect from this should be 1. So we execute this cell, and we see that the true value is indeed 1, as we expected. And that's because in this simulation here, I'm assuming that the underlying hardware doesn't have any noise. So we are in the ideal scenario. Now let's see what happens when we start to add noise to the circuits, or to the hardware, or we run it to a real hardware that has a noise that we don't really know what to expect. So in this case, again, I'm running the circuits through a simulator, but in this case, I'm simulating also a noise. In this case, the polarizing noise, which I'm tuning to some level. So with some less than 1% probability, some of the gates on my circuits will just act as identity gate instead of acting as the gates that we want them to be. So at the end of the circuits, we will not have, when we go and measure the final state, we will not have something that with high probability, something that is the same as we started with. So it's not going to be equivalent to the identity again. So let's actually run a simulation where the noise level is 0.005 and see what happens here. Yeah, so as you can see, the true value before was 1, but as soon as we added a little bit of noise here, the noisy value becomes very far from 1. It's like 0.625. So, let's imagine you are running a real algorithm solving an actual problem, and now you have a value that you don't know whether you can trust or not, because it's very far from the true value, and obviously it's a value that you don't know in advance, like in this toy example. So this is where quantum error mitigation, and in particular zero noise extrapolation, will come into action. So what I'm going to show you here is that you don't need to practically do any of the steps that Jordan was talking about. So you don't need to manually scale the circuits or add noise and then interpolate. You can literally just import the ZNE package module from Mythic and just run ZNE.execute with ZNE. You pass the circuits, you pass your executor function, which is the one that will run the circuits on the hardware machine, or in our case, on the simulator. And then you just say how you want the noise to be scaled. So in this case, folding the unitary gates globally. So it was already in one of Jordan's slides, but let me iterate here. Yeah, so remember, the idea here is that we want to try to increase the noise. Let's say G, the G you see here is the original circuits, and now we want to see what happens when the noise is bigger. So we increase the noise by 1 time, by 2 times, by 3 times, and then we interpolate back and see what happens at the zero level. You will understand this by the by the end of the demo, hopefully. But so how do we increase the noise of G? So increasing the noise is easy. Like removing the noise is hard, but increasing it is easy because we can just, like in this case, fold the circuits, which means we can run the circuits G, then run the inverse of G, and then G again. So all of these things you see on the right is still equivalent to G, but now it will be more noisy than G because it will have like 9 gates in this case instead of like only 3 gates that we started with. So global folding means that you take the whole circuits and then you inverse and then you have another copy of the circuits. Whereas another technique is local folding, where you do the same game but only at the level of the single gates. So in the picture below now, G is a single gates, and you have G, G dagger, G, so the inverse of G and then G. So the second and the third becomes identity. So this is really equivalent to G. So the circuits is like, as a unitary is equivalent to the one you see on the left, but now again, you have more gates and therefore more noise because, each gate can be noisy. We are adding in our example, the polarizing noise. So each gate contributes to adding the noise on the circuits. So going back to, let's check if there is any question on the chat. Yeah, going back to our demo, let's say we want to execute the circuits running zero noise extrapolation. And in this case, we fold the gates globally. So the picture you saw on the top of the slide. So, and then we will just print out the ZNE value. So the expectation value that comes from running the same measurement that we were doing above. So remember, the ideal case was 1, the noise value was 0.6, and our goal is to be as close as 1 as possible if this is working fine. Here I'm also printing the distance between the true value, which once again it was 1, and the noisy value, and the same for the value that we get after applying error mitigation. So let's see what happens. Again, I'm running it on a simulator, so it's quite fast. I'm not making any, call to any real hardware. So yeah, that's successful because we have something that is much closer to 1. In fact, it's like, 0.043 far from 1, as opposed to the noisy value, which was like 0.374 away from 1. So we definitely made lots of progress. Obviously, as we were saying before, is at the cost of running circuits that are bigger. So let's assume this was on a real hardware, then you are spending, for example, more money to run these circuits with error mitigation. And also you are running more version of the circuits because you are running it on the scaled folded once, then folded twice, then folded 3 times, etc.
Hello.
Yep. Is there a question?
Sorry, I'm a bit confused here. You see,
Okay.
when we have our circuit, we run it and we get our true value to be 1, right?
Yes. Yeah.
Yeah. After that, I will amplify the noise, and then we get a noisy value which was a bit lesser, and then we encoded it. We added the zero noise extrapolation method, and it increased to about 0.9. So I'm confused. The one that we get as a true value, like where was the noise there? Like I don't know.
So maybe let's restart from here. So what we are running is we start from this state, so the 0 state. Well, in this case, it's 2 qubits. So we start from 0, 0 here. We run the circuits and then we measure the first qubit. And we measure against this observable here. So the expectation value, if this, we assume this is a unitary, then the expectation value is 1. So the true value is equals to 1. So, and here we are running without any noise. Now we adding noise and we do the same thing, the same circuits. The circuits has not changed, but now the expectation value is like much less than 1. Is it clear so far?
So I don't know, the expectation value, is it it's like I don't get that part, the expectation value. Like what is
Okay.
that one?
Yeah, so let's say you have an observable, so you are measuring against, so maybe I can draw here. So let's say you start from these states. Copilot. Yeah, so and then we do our circuits, we run our circuits, and then we measure against this state again. So the expectation value is the probability that we get, basically is the probability that we get these states, because that's what we are measuring against. And then the probability to get this state in this case is 1.
Okay, so where is the disadvantage of this one? Because why do we have to apply noise and then bring it down?
Okay, I think maybe I understand what is confusing here. Yeah, so now I'm not applying noise on purpose. I'm just simulating it with noise. So this scenario you see here with the noiseless, it's an ideal scenario that you don't have in real life. Like in real life, if you run a circuits on a quantum computer, you actually have noise. So in the second cell here, what I'm simulating is the same noise you get on a real hardware. So maybe ignore all of this one that I'm highlighting here. Just imagine you have the circuits and you send it to a hardware, so to IBM hardware, for example. And then you do the same thing. You want the expectation value that you get back. What you will get back in this case is like not 1 anymore. So I'm not, I'm not applying here. I'm not doing any error mitigation yet. I'm just showing you what will happen when you simulate, when you run the circuits on a real hardware. Now, the only thing that may be a bit confusing is that I'm not running it on a real hardware, but I'm simulating the noise myself.
Okay, thank you. It's clear now.
Okay. And yeah, so once you have the noisy value, then, once you see that, once you know that your hardware is noisy, you want to fix it with error mitigation. So one thing that is maybe that could be not clear is that you don't really know what the true value is in the beginning, because you are just, running an algorithm and you want to find the solutions. But you know that your hardware is noisy, so you don't know the exact, how much is, like in this example, we know what the true value is, but in reality, you don't know what the true value is. So, but you can assume always that your hardware will be noisy and that you will need error mitigation. And here I'm just showing on a toy example why how it works. So yeah, and really executing zero noise extrapolation, so error mitigation on MITIC, is as simple as running these 4 lines of code. And the rest is like taking care behind the scenes by MITIC. So MITIC will do the execution on the hardware and everything. It will scale the circuits. It will run all the circuits scaled to the hardware. It will get back the result and interpolate it. And at the end, it will return you this value, which I'm calling it ZNE value. And as I'm showing it, it's actually effective because if you compare it with the true value that we had in the beginning, that's much closer to 1 than the noisy value. So it seems a bit that I'm cheating because I'm adding noise myself and then comparing it with the ideal value. But that's just for the sake of the demo, because if we see the value, if we already know the value, then we can see the efficacy of ZNE. So Jana is asking, is our goal to get more noise or less noise? Yeah, that can be confusing as well. So let me go to this slide here. So what we are doing is adding more noise artificially so that we can extrapolate back to the case of zero noise. So the ideal result is when we have no noise. So yeah, bear with me and let's try to follow this graph here. So let's say we are on the normal case. So the noise scale factor is equals to 1. So right now, this is our original circuits. So we are not doing anything. So the first dot here. And then we run it on a real hardware and we get 0.6, which is the one you saw in the demo. Now what we are doing is like we artificially add more noise so that we see what happened in the case of, yeah, for example, we double the noise and we see what happened in the case of noise scale factor equal 2. And you see the expectation value is even worse than before compared to the true value, which was 1. So, and then what we do is like we take these data points at noise scale factor 1, 2, 3, and so on. And then we extrapolate back to the 0 noise scale value, which is the ideal scenario, which is the answer we actually want. Does that make sense?
Yes.
Jana, not yet. So what in particular?
Hello?
Yep.
Yeah, can I come in? Maybe when I explain to my colleagues, they may understand what is happening. From my understanding, my understanding, the first code we ran that gave us the one, that was the unitary. It's an expected value because the unitary is just like the identity, which is 1. So now we are trying to see what happens when noise comes into the codes or into the system. So when there was noise in the system, so we actually introduce. So it's like you introduce the noise to see what will happen to the expectation value. And really it affected the expected value, which is 0.6 and thereabouts. So now we are trying to mitigate, to take off the noise we put in. So now the third code that is now explaining how to bring or how to take off the noise that we introduced. And that is giving us the expected value to be 0.9, which is almost closer to when we had our exact value or expected value to be 1. Can I understand?
Yeah, so the final goal is to get the ideal value. So in some sense to eliminate the noise. But we do it maybe in a bit counterintuitive way, which is so obviously, there is no magic way to, if you have a quantum computer that is noisy, there is no way to just take the noise out. That would be too good to be true. So that's why behind the scene, what we want is the output of the algorithm when you run it on a hardware that has no noise. Unfortunately, nature is so that we always have some noise, or at least the engineering at the moment, quantum engineering is so that we always have some noise. So behind the scene of error mitigation, what we do is this trick of like increasing the noise, because increasing is something we know how to do, is decreasing the problem. But then we extrapolate back all the way to that 0 case. So yeah, hopefully it's a bit more clear now. Yeah, so again, unless you are working on error mitigation or contributing to Meetic, if you are just using Meetic, you don't really need to care what happened behind the scene. You just have a circuits, you have a function on how to execute it, and you just run this function, and you will have a value that it's better than the noisy value. And that's really all you care about as a user. With a caveat that, back to one of the questions in the chat was, what are the practical challenges of using error mitigation with Meetic? One of the things we mentioned is that now in this example, we were lucky and we got a pretty good value that was close to 1. But sometimes the technique is not as efficient. And one way to make it more efficient is to tune the parameters. And one parameter is the way we fold the gates, the way we increase the noise. So in this example here, I was using the global folding, which is, going back to this slides, is the technique above. But there are cases where for some particular kind of noise, or maybe the circuits are some particular gates, so the local folding may be better. Or there are even other techniques of stretching the noise that are better. So one thing that one is to learn as a user of Meetic, or in general of an error mitigation package, is how to tune the parameters so that the technique is effective against the circuits and against the hardware and the noise model we are running. So in the rest of the demo, we will see some of this technique. So right now we have these results, which is pretty good. It's yet not 1, is not the ideal value, but is much, much closer. Now let's try to tune, again, as a user, not as a Meetic developer, let's try to tune the parameters of the technique. And the first thing we can do is changing the scale noise technique. So this is just a fancy name for local folding. So again, the one on the slides at the bottom, which is different from global folding. And in this case, it only happens with a random number of gates. It doesn't happen with all the number of gates. So I'm just changing, compared to the snippet above, I'm just changing this argument. And I'm not implementing myself. I'm just using one from the Meetic libraries. And I'm running it again. So you can see it actually, the error got slightly worse. So, perhaps it was not a great idea in this case. And it means global folding globally was more effective than local folding at random. So something else we can try is the interpolation method. So let me go back to the slide. So I explained this concept of like scaling the noise and then interpolating back to the 0 noise factor. But, as you know, there are many ways. So given a set of data points, there are many ways we can extrapolate back the the 0 point. So let's say you have, these 3 data points. They should be the same in both slides. I think the axes are scaled a bit differently, but the blue points are the same on both graphs here. So, and, we can fit those points with a linear function, and that will give us that on the 0 case, the results will be around 0.75 or something. Or we can try another kind of extrapolation, which is like fitting against an exponential function. And we see that in this case, we'll actually be almost perfect, almost close to 1. So for this example in the slides, the extrapolation that we use actually makes a huge difference. Let's see how to change this in Meetic. So we have this concept of factory that you can read about more in the documentation, but it doesn't really matter too much. What matters is that in the factory, we can express what kind of function we fit the data point against. So in this case, we are using an exponential factory, which means we are fitting against an exponential function. And we are also saying that the scale factors that we are interested on are 1, 2, and 3. So we want to scale the noise 1 time, 2 times, and 3 times. The default value, so in the previous snippet, we didn't specify a factory. So that means that we were using just a polynomial fitting or a linear fitting. I don't remember which one is the default. But let's see what happened when we change to exponential factory. So you can see that just like in the slides, the error now is like 0.001, which is much, much closer to 1. So let's print explicitly that ZNE value. So we basically, just by running, remember the device has always the same level of noise. So the simulation is always happen with the same level of noise, but now just by applying error mitigation, we went from like 0.6 something to 0.999, which basically very close to the ideal value. And actually, we can see the graphs that I copied in the slides are actually coming from this function. So we can actually see live. We take the factory, which was the exponential fitting. We fit against this point, and we see that it behaves so well because it actually can interpolate that the 0 value as expectation value equals to 1. Or 0.99. So another thing that we can change is actually the number of time with samples. So we can take the execution, run it a number of time, and then take the average of the expectation value. That's another parameter. We can run that. Obviously, since we are running it more time, it's taking a bit longer. But yeah, we do have very similar value. It's a bit worse only because, it's all of this is probabilistic, so you don't have the guarantee that you have exactly the same. The noise itself is probabilistic, so you don't have the guarantee that is always improving, but we have something that is, again, very close to 1. So as a recap, what we saw so far is like how to create a benchmarking, a circuit that we can use to benchmark the technique. Again, this is just for the demo, but in your case, as a user of Meetic, of any error mitigation package, you will have your own circuits that you want to run that is compiled based on the algorithm that you are running and the problem that you are solving. Then we run it on a computer, on a quantum computer. We saw that because of the noise, we have a value that is not really close to the ideal value. We used zero noise extrapolation to improve on that value. We were still not super happy with the results, so we tried to tune the parameters. We changed the folding. It didn't have a big impact. In fact, it had a negative impact, so we went back. Yeah, actually here we can, since we found out that global folding was better, we can actually use global folding. Again, we will not get values that are always, monotonically better or worse, but you can see that with a new extrapolation, we are always much closer to 1 than the polynomial extrapolation. So we tune the extrapolation, we tune the folding, and then we increase the number of samples. Maybe this is a good time for question. I see there is one on the chat. So does that mean that interpolation is more efficient than extrapolation? No, yeah, sorry. I've been using the two terms to mean the same thing. But maybe let's stick with one term, which is extrapolation. I guess in this, with regard to this context, there is not really a difference between interpolation and extrapolation. But the thing I wanted to highlight here is how exponential extrapolation is better than polynomial extrapolation. So let's stick to the term extrapolation. Everything we are doing here is extrapolation, even though sometimes I'm calling interpolation. But what I'm highlighting it here is that exponential was better than linear. And notice that you may wonder, okay, is it always better? If it's always better, why isn't it the default? And the answer is that it's not always better. It really depends on the model of the machine you are running the circuits against, the specific circuits like the gate set that you are using, the complexity of the circuit. So, how depth it is, how many layers, how many number of qubits. All these things will have, for all these scenarios, there will be values of the parameters, including like extrapolation parameter that will give you a better fitting or a worse fitting. And there is no perfect science for that. It's more like you will have to play with the parameters, understand for your scenario which one works better and which one works worse. There are things you can assume. For example, we know that the polarizing noise has an exponential decay. So if you apply the polarizing noise on one gate, on one layer of gates, and then again you apply on another layer of gates, it decreases, it deteriorates, the noise deteriorates exponentially just because it's compounding layer by layer. And that's really the reason why here the exponential function will fit better than the linear or the polynomial function. I hope that clarifies. Sorry for the using the terms interchangeably. So, any other question on the?
Hello, sir. Hello, can you hear me?
Yeah,
please?
yeah, I can hear you.
Okay. I was what I would like to know is that is there any way or anywhere we can learn more about the Mythic library so that we know which one to use for maybe particular purposes, or the Mythic libraries? Is there anywhere we can study them further?
Yeah, definitely. The documentation I was showing you in the beginning. So if you go to meetic.readthedocs.io, yeah, just this link here. I will post it in the chat. So if you go to this link, then you click. Well, first of all, there is a very basic example, which is similar to the one I'm showing it to you on the demo. But also, if you go to user guides, it's quite comprehensive, going through all the parameters, all the techniques that you can use, and it explains them one by one. So the whole library is basically explained here.
Thank you very much, sir.
And yeah, so finally, yep. One more question.
Please, I wanted to ask, so far, there are many classical quantum algorithms that I've seen, and then mostly when I see them, they are written in Python, and you see, some languages like C++ has faster execution than this Python, and I don't know how does that one affect.
Yeah, so if I understand the question is like, why are all these things written in Python instead of a language that is more performant, like C++ or like Rust? Yeah, so maybe one, I don't know if I have a brilliant answer for that, but obviously there is some legacy in the fact that most of the quantum domain languages are in, all the toolkits are in Python. So that's one reason why Meetic specifically was written in Python. So if you want to write circuits for Google Circ, for IBM Qiskit, for Amazon Braket, they all use Quantum. So it's easy to use Quantum, to use Python to integrate with those toolkits. And then maybe the second answer is that right now we are using Python. I mean, in this demo, you see Python being used mostly as on the front end side, in the sense that what happens behind the scene could happen in other languages as well. So if you want something more efficient behind the scene, you can have the API and the language to be in Python, but then what happens inside the function could be C++, for example. In the case of Meetic, we actually write everything in Python, including the behind the scene and the backend, but you can potentially write it in another language. So, and the third point is that remember that here everything looks very fast because we are running on a simulator, we are running on only 2 qubits. The circuits is like pretty small. It's like, I don't know how many layers it is, but it fits into almost into my screen here. So maybe 40 layers. But in real life, you will have something that is much bigger. And also remember that you are executing on a real quantum hardware. So you are maybe sending it to the cloud, executing it, then getting back the value, then sending the scaled up version of the circuits, getting the value. And the actual execution happens somewhere else. It doesn't happen in Meetic. It doesn't happen on the machine or in the language that you are running Meetic on. So I would say that's a bigger bottleneck than the one of doing error mitigation. So the actual part that does error mitigation, the skeleton of error mitigation without including the execution is written in Python, but maybe it doesn't matter that that one is slow or fast, because the bottleneck anyway is the execution of the different circuits in the backend. and that's happening in actual quantum hardware. So yeah, I hope that answered the question. But if you want to rewrite part of Meetic in C++ or Rust, you are very encouraged to do that. That would be a cool project also for learning.
Also, I don't know if Alessandro already mentioned this. I might have missed it, but for instance, Qiskit, their transpiler, now the backend is written in Rust, so it speeds things up in that case. And like I guess like one of the reasons that like most front ends tend to be written in Python is that most quantum computing people have a physics background and not a software engineering background, and so most of them would be a lot more familiar with sort of scientific computing with Python as the kind of primary front end. So I'd say that's another kind of like historical reason for it.
Yeah, and even technically, there are things like when I said we do an exponential fitting of the function, we are basically using a NumPy library, which is or this kind of scientific library that you already have access to in Python, and that often, like probably the fitting in that library is not even running in Python; it's probably running in C++ already. There is another question. Does the number of qubits affect the noise output? Yeah, definitely. So it's in basically any noise model, the error at the end will be a function of the noise level, but also of the complexity of the circuits, so the number of qubits and the number of layers. So the number of gates, the depth and the number of qubits. I mean, as a maybe approximation, you can imagine that each of these gates here adds a bit of noise to the circuit. So imagine if you have more than, I don't know if you can generate, I guess in this example, I can only generate 2 qubits, but yeah, obviously if you have a circuit with more qubits, you will also most likely have more gates, and that will make it more noisy.
You could try a different benchmark, like benchmarks.something else.
Yeah, maybe virtual.
This I don't know. Is there an instance where the noise is not really proportional to it's not like the scaling part where we graphed it and it was proportional, and as you increase the number of qubits, the noise proportionally increases. So I was saying, like, is there an instance where it is not proportional to each other, the noise and the qubits?
Yeah, so I'm not super expert of all the noise models that there are out there. The proportionality between the number of qubits and the noise is definitely always there. It's not always the same, and that's one of the reasons why we need to fit things differently. So you can have a linear proportionality or like an exponential proportionality, but I don't think there is any case in which increase the number of qubits. I mean, most of the noise comes from interference between the qubits in the hardware. So the more qubits you have, the more entanglement between the 2 qubits you have. Generally, the more noise you have at the end.
Thank you very much.
I'm trying this just for fun. Oh, interesting. We call it num qubits here and n qubits here. Oh, wow. Yeah, this is an example of circuits with like 4 qubits and very strange gates. And try to run simulator. The value is again 1 because these are benchmarking circuits that usually they correspond to identity. The noise value in this case, it's smaller. But yeah, it's hard to compare because we changed the depth, we changed the number of qubits, but also the nature of the circuits is completely different. So maybe we can try to change the number of qubits on the same circuits. This should be again 1 or close enough to 1. Hopefully this is going down now. Yeah, from 0.8 to 0.64 just by increasing the number of qubits. I mean, it's just one example, but I guess generally that's the case. So the very last thing, so before taking the question, I left you with this run through all the parameters that you can set on Meetic and that you can set on zero noise extrapolation. And then you're wondering, okay, how do I find the perfect parameter? So, and as I was saying, there is no way, it's not an exact perfect science where the noise model perfectly, which is already a challenge in itself. But then even if you do know that, there is no perfect science to understand what parameters you need to use. However, in Meetic, there is a tool which is called calibration calibrator, which gives you a sense of like, given your noise model or your hardware, what parameters you want to pick. So maybe ignore this cell here, which is just like a technicality. So I'm basically running the circuits, but I'm not measuring against one specific observable, but it doesn't matter much. So what I want to show you is that calibrator will give you a nice table where it will run your hardware, which is defined by this execute function. Again, in our case, it was a simulator, but just imagine it's a real hardware. And then it runs all these benchmarking circuits against all the strategies, and it gives you, in the third column here, the performance of the particular error mitigation technique with that particular set of parameters. So you can see that with our particular hardware model, which has a depolarizing noise of 0.005, actually ZNE with linear extrapolation with this scale factor and with this scale method will bring the error from like 0.04 to 0.033, which is like a 12-fold improvement. So it gives you a hint of, maybe these are good parameters. And yeah, it will not, not always give you the best strategy, but it can guide you through finding good parameters. You can ask for the actual best strategy, but again, it will be based on like these sets of benchmarking circuits. So we can check what it is in this case. It turns out for our hardware model, which we are simulating, the best technique is ZNE. best extrapolation is something called Richardson extrapolation, which is basically a polynomial extrapolation on the on a number of with a degree that is equals to the number of scale factors. The scale factors are apparently the best strategy, and the best strategy to increase noise is folding gates globally. So, and once you have the best strategy, you can directly apply the calibrator with that strategy on your circuits, circuits we defined before. We can see what happens here. I guess we changed the circuits now, so I'm not sure what is really going to happen. But yeah, or if it will ever finish. Yeah, and the very last thing is that all of this was for zero noise extrapolation, which is one of the many quantum error mitigation technique. But MITIC offers other a bunch of other techniques as well in the library. One of them is probabilistic error cancellation. I see we are running out of time, so I'm not going to go into that. But again, you can go to the user guide. We have a full user guide on probabilistic error cancellation, and maybe you can play around with that with your circuits and see if it gives you improvement or not compared to zero noise extrapolation. So it actually runs in many seconds and gives you this value. But again, we did played with the circuit, so I don't know what it means anymore. Anyway, yeah, this concludes the demo and the session. Thank you everyone for attending, and I'm happy to take some questions.
Okay. Thank you very much, Alessandro. So we'll wait for some few questions. So if you have any question, please, you can ask.
Here, there is a question in the chat. Can ZNE be used in machine learning? Jordan, you want to take this one?
Not that I know of. I haven't ever heard of it being used in machine learning.
So do you mean quantum machine learning or like classical machine learning? Because I mean, this is all about noise in classical. Yeah, I guess you will have to define some concept of noise there, which I don't know what it would mean exactly. And yeah, to be fair, I'm not sure if it's a technique that was genuinely invented as a quantum technique, or it comes from some classical technique from some other field. I'm not really sure. But all of the thing we talked about today is really in the context of noisy quantum devices.
But that said, a lot of techniques that are invented in physics end up being really useful in other computational fields. So yeah, that is always a good thing to kind of ask, can this be applied somewhere else?
Yeah, and there is obviously the all quantum machine learning field, so which is really just a way to run. Yeah, I mean, I don't want to get into the details, but one thing to point out is that the technique we showed here is really like sort of agnostic of the application you have. So you can really input any circuits you want, including circuits that represent your quantum machine learning algorithms, if you have something like that. And it will, mitigate the noise there.
Okay, thank you very much. I think our time is up. So Jordan, Alexander, thank you very much for honoring our invitation, and we hope to see you in future sessions.
Yeah.
Thank you, Henry, for inviting us. And yeah, thank you everyone for attending.
You're welcome.
Yeah, please do feel free to join our Discord, ask any follow-up questions if you'd like. Cheers.
Okay. So participants, bye. Participants, I think we have a session on Wednesday, and I hope to see you. If you have any other question in relation to the management or the project and anything, you let me know, or you can send us an email. So Thursday we have a few presentations from the mini group. So I will invite you to meet your project supervisors and then mentors, so that you can then wrap up some presentation for Thursday. Good. So I think I have a meeting with some groups. I've already sent you messages, so we'll discuss about the best time to meet and have our session. Thank you. See you Wednesday.